our talk will be about to pin or not to pin, which is basically an evaluation of the applicability of certificate pinning for or in Android apps. My name is Sascha. This is my colleague Yasemin, and we will present joint work with Marten, Oltrogge, Sergej, Dechand, and Matthew Smith. And yeah, we will both give the talk. So I will present a part of the slides, and Yasemin will present other parts of the slides. So,
to give a small outline, first we'll talk about how TLS certificate validation works on Android. Then we'll give a brief overview of a previous work of the last years, which posed the question whether or not pinning can help fix TLS on Android. We'll talk about the requirements to implement pinning on Android, and then show the large-scale analysis that we did with 600,000 Android apps. For them, we found out who could use pinning. We talk about who of these should use pinning. We compare these suggestions to the status quo of how many of them already implement pinning. We will explain to you how we talked to developers about why they did or did not implement pinning and their suggestions. We'll briefly explain the limitations of our work to you and conclude with takeaways.
Okay, so how does certificate validation on Android work? It's basically pretty much the same as it is in web browsers. So to establish a secure TLS connection in an Android app, a server needs to show a valid X509 certificate, which was signed by a trusted certificate authority. And a trusted certificate authority is one which comes pre-installed with the Android operating system, and at the moment that is about 130 CAs that come pre-installed with Android. And as long as developers or servers show such certificates, everything is fine. In case they want to use an untrusted certificate, such as a self-signed certificate or one that was signed by a different CA, a custom workaround is needed. And on Android, such custom workarounds require developers to implement custom trust managers, and they can be used to, for example, improve security by implement pinning, which we will explain later on, or they also can be used to totally break TLS security. Our current work is based on previous work, and part of that previous work is our own work. So we had a CCS paper in 2012, Why Even Mallory Loved Android, which was an analysis of Android apps in terms of their SSL security. And there was another paper that analyzed the security of SSL in software in general. Both were CCS 2012 papers, and they concluded with the results that as soon as developers touched certificate validation and implemented their own certificate validation, they usually broke their apps and made them vulnerable to man-in-the-middle attacks. And then we had follow-up work in 2013, which basically was about how to redesign the development of SSL in an appified world. And we made the proposal that instead of requiring developers to implement custom solutions, letting them configure their verification, for example, to just have a configure flag that allows to use a self-signed certificate in a secure way. We will now give a brief introduction of pinning on Android.
So what is pinning? When you pin, you effectively limit the number of trusted service certificates for your connections. You will then only trust a list of hard-coded or configured certificates, and you can either pin leaf certificate information or CA certificate information. You would want to pin leaf certificate information if you, for example, operate one self-signed certificate and you want to use that. And you might want to pin CA information if you, for example, want to trust CA cert, or if your company runs a custom CA. but the decision whether or not to implement pinning is a trade-off. On the one hand, pinning increases security, so as soon as you pin, you remove the weakest link property from the current CA-based TLS ecosystem, so that if a CA gets compromised, you don't suffer for it. On the other hand, implementing pinning decreases the maintainability. So whenever a certificate updates, users need to install updates to get the new pins, and until they do that, your app won't work, or your TLS connections in your app won't work. So let's talk about what is needed to make connections pinnable. First of all, you need to have hard-coded network origins. So you need to know the certificate information that you want to pin in advance. It either needs to be hard-coded into the binary, or it can be given in a configuration file, but it needs to be known before the connection is set up. You also need to own your code. So developers should control the API calls for the TLS connection establishment. And this is not true for shared code. If you do your TLS connections via third-party libraries, you don't own the code and you can't control when certificates change. You also can't use pins to secure shared network origins. So you need to have control over the certificate of the target network origin. And this is not true for shared origins like Facebook. You can't control when Facebook uses a different CA to sign their certificates or when they roll out new certificates.
Okay, so now that we know what is required to make a connection pinnable in theory, we were interested in a couple of questions. So we had a corpus of 640,000 apps from free apps from the Google Play Store, and we were interested in how many apps could and should pin all or parts of their connections. We were interested in the question of how many apps actually use pinning right now, and in case we came up with or we can recommend to use pinning, we wanted to know which strategy is advisable. So is it advisable to pin a leaf certificate information, or is pinning root or just CA information the better idea? So the general question is, can pinning be rolled out to actually fix the weakest link in the TLS infrastructure? So, and what are the challenges when pinning should be rolled out globally in the Android universe? So the question is, who could use pinning? And to answer that question, we were, as just explained, interested in who owns the code that establishes TLS connections. So that would be the question whether does TLS connection establishment happen local to an app's package name or the main activities paths. So if that is the case, then ownership is given and pinning can be used. If not, ownership is not given and pinning is no good idea. We were interested in finding shared origins. So in case an origin is used across apps of different developers, we think pinning is not a good idea, so we just gathered all origins we could find in our app corpus in case the origin was used across multiple apps. Exclusivity is not given, and again, pinning is not a good idea. In case it is just specific to one app or two apps of a specific developer, exclusivity is given and pinning can be used. Then again, we were interested in the fact whether the network origin is already known at compile time, so is included in an app's binary or is configured or is given in a configuration file. If so, then control is given and pinning is a good idea. If not, pinning is not a good idea. So we started by analyzing our apps and checked for code ownership and the shared and hard-coded origins questions. We were mainly interested in identifying the input parameters for TLS connection related Android API calls. So what we wanted to know is, just to illustrate that, is the URL or origin string that the Android API, such as URL objects or socket objects or the Android web view, uses to establish a network connection. How could we, or how did we actually identify input parameters for the TLS connections? We used the Oltrogge tool to decompile an app and then created constructed call graphs for our apps in our app corpus. We checked the call graphs for TLS connection related API calls, so we checked the call graphs for objects, URL objects, web views, and stuff like that. We conducted a reachability analysis and only continued our analysis with objects that were reachable, that were actually used. We gathered origin information by applying static code analysis techniques. Therefore, we used backtracking and program slicing. I'll give you a short example of string concatenation. So just imagine there's a developer that wants to connect to HTTP example.com and uses the protocol and the host in two separate strings. And he could do so by just concatenating the protocol and the host string and input these two values to the URL constructor. And once decompiled, the Dalvik instructions would look like this. So in line 17, a URL object is constructed, and then we track all the inputs that actually affect the constructor parameter, and we collect then in line 12 and line 7 the substrings, see that string concatenation happens, and finally come up with the complete string. Just as a brief overview. More details are actually given in the paper. Mm-hmm.
Now that we've considered who could use pinning, we want to come to the question who actually should. We analyzed these 600,000 free Google Play apps from October 2014, and they established 20 million network connections, which we analyzed. First of all, we checked if the origins were hard-coded to be HTTPS origins. So that was true for only 1 million of these 20 million apps. Twice as many were hard-coded to be HTTP, and the majority was not hard-coded but depended on user input or other stuff at runtime. So only 5% of all the connections that we saw are even eligible for pinning. So that were the ones that we considered in our further analysis. The other thing we wanted to check was if code ownership was given. So of this 1,900,000 were connected via third-party libraries, and only 145,000 were in custom code. So 86% of all these hard-coded 1 million HTTPS origins were found in shared code, and only 14% of them were found in custom code. So these 14% were the ones that were interesting for our further analysis. The last thing we checked was if the origins were shared or unique, and found that only 45,000 were unique. So altogether, 4.25% of all hard-coded HTTPS connections were found in custom code and connect to app-specific or developer-specific origins. And so therefore, conservatively, we can only recommend these connections to be pinned. Then again, we had these 16 million connections for which we didn't know whether they were using HTTP or HTTPS, and we just extrapolated. So optimistically, some of them could be HTTPS, and we would find out at runtime, which we couldn't. So in that optimistic case, extrapolating, we could advise to pin 140,000 TLS connections.
So now that we knew how many apps actually could benefit from using pinning, could make their connections more secure, we were very interested in how many apps actually do that. And just a little spoiler, it's not that much. Not that many apps. To answer that question, we used Melodroid, which is a tool we developed for our CCS 2012 paper, and we extended it. And we were interested in finding apps that implemented custom key stores. A key store on Android is basically an object which can be used to store CA certificates, to limit the number of trusted CA certificates, and for apps that make use of custom trust managers to change the default validation behavior. Out of our app corpus, we found just 21 apps that used an own key store to limit the number of CAs. That 21 apps, 18 apps, I think, were using CA cert, and 3 apps were using custom root CAs. And another 24 apps used a trust manager that implemented pinning. So overall we found 45 apps in 640,000 apps that currently implement pinning. So obviously there is some room left for improvement.
To sum it up, we had analyzed 640,000 apps, of which 230,000 hard-coded 1 million TLS connections. And that whenever the origins were hard-coded and not shared, we recommend pinning. Therefore, we recommend pinning for 45,000, which is 4% of the connections, or 11,000 apps, which is 1.8%. If we go about this a bit more optimistically and extrapolate, we suggest pinning to be considered for 140,000 connections, or about 60,000 apps, which would make 10% or 9%. However, pinning is implemented currently for 45 apps, and we wanted to know what we had to do to close the gap. So we want to boost that number. What we did was talk to developers. Of the apps we had identified as eligible for pinning, we contacted 500 developers. 45 responded, which wasn't too bad, so we didn't offer them anything, just asked them to kindly help us and asked them a few questions about pinning. And 3/4 of them lack even the most basic understanding of pinning. So they either had never heard of it, or they said they had heard of it, but when we asked them what it was, they couldn't tell us. Of those who knew a bit about pinning, they associated many problems with it. The worst problem was the huge trade-off. So they said the maintenance effort is too high. They were also missing support. They were missing libraries. They said they wanted easy out-of-the-box solutions, and most of all, they missed example code, or code that was ready for them to copy and paste. Also, they said they feared to alienate users, so that whenever something changed, they would have to rely on users to update their apps immediately, otherwise the apps would stop working and people would probably just get rid of the app. What we did was we developed an easy-to-use web browser-based tool to help developers decide which connections to pin. And this tool also offers code examples that can just be copied and pasted. You can try it. Some of the developers tried it and liked it. Oh yes, and but one thing they said they were correct. So when they would have used pinning, that could really potentially kill their apps. From a previous cooperation with Sonar Antivirus, we had collected data on update frequencies of third-party apps. And what we found was really bad. So only about 40% of the people using third-party apps, on average, updated them on the first day an update was available. And it really stretched out. So it took about 30 days for 70% of the people to update their app, and it took 220 days until everyone had updated their app. So there were a huge chunk of people who would have not working apps if the connections would have been pinned and if the pins would change.
So yeah, our work is limited in multiple ways. We couldn't categorize all connections due to the fact that a huge fraction of origins were not hard-coded in an app, so we just couldn't tell whether pinning was a good idea or not, and we couldn't classify those connections. We tried to make an effort to account for this by splitting up our evaluation into an optimistic and conservative part as just described. And our results might suffer from underreporting due to the inability of classifying a kindly huge fraction of connections. We might underreport the applicability of pinning. Again, reporting optimistic and conservative results it might help here. And we also didn't analyze native and obfuscated code, so whenever an app, I don't know, includes OpenSSL to use for TLS connections, we didn't analyze those cases. As takeaways, we can say pinning is advisable and should be implemented in some cases, but it does not solve the security and usability shortcomings of TLS we have currently. To actually help for maintenance and the update frequency problems, we would recommend, instead of hard coding pins into apps binaries, deploying pins via configuration files that can be more easily updated than a whole app. And we also think that instead of recommending pinning again and again, approaches such as Google certificate transparency might look a bit more promising to actually make the TLS universe more secure.
But to close the gap between these 5% of apps that should use pinning and those 45 apps altogether that actually do, we need more support for developers. And our tool goes in that direction by helping developers with deciding whether or not to use pinning and with offering code examples, and you can try it. Also, a tool like Let's Encrypt can help admins to easily obtain and use free CA-trusted certificates, so that might be another direction that helps instead of pinning. Thank you for listening, and if you have any questions, feel free to ask.
I'm Marten from Rakuten. So we have actually went through all rings of hell with certificate pinning. Start pinning like leaf certificates, then Heartbleed happened, so we had to reissue all apps, and of course Apple took like a week to reissue all apps, right? So then we started pinning CA certificates, but then CA certificates started switching their intermediates. So we ended up with actually approach of using self-signed certificates for everything and then pinning CAs for the self-signed certificates. And actually for commercial certificates, wherever it's applicable, we implemented soft fail. So application doesn't really fail if pin doesn't match, but it notifies developers that something suspicious is going on. So in this case, like if our apps fall into your classification, then you would probably misclassify us because we don't fall under your categorization of apps, in particular the soft failure part. So would you implement into your recommendation, please? Because a lot of apps would fail if you just pin certificates.
So what I understand is you say that we underreport the number of apps that already use pinning because we didn't find you in the way that we searched?
I'm pretty sure you didn't, yeah, because like we pin certificates sometimes not in a way, we re-implement trust store. We just verify the fingerprint and then, if it doesn't match the fingerprint that is hard-coded in the app, then we just report it. We don't really force TLS stack into trusting only one certificate.
Okay, we're glad that more people actually use pinning than we found, but we're pretty sure that your solution is a custom solution. So I hope that more people use it, but we still think that even if it's not 45 apps that use it, but like 400 apps, it's still bad.
Oh no, I totally agree. That's totally bad. So thanks for yours.
Adam Langley, thank you for that talk. You keep saying certificate pinning, but it's not. It's public key pinning. If you pin certificates, you're doing it wrong. So are you pinning public keys?
Well, actually, you could pin both, right? You could pin.
There's lots and lots of subtle issues with pinning certificates that trip people up. There's lots and lots of subtle issues with pinning public keys as well, but there's less of them.
Well, with pinning a public key, you're a bit more flexible. You can basically switch the certificate and still keep the same public key. But in some way, it is limiting the number of certificates you trust, right? Or number of crypto items you trust.
So for one example, you can't, for example, with certificates, you can't tell what intermediate certificates you'll get because CAs have multiple copies with, say, different expiry dates with the same name. And, chain building is non-deterministic. So if you pin a certificate, you get odd, random errors on certain devices and so forth. So just in general, you should pin public keys and not certificates. Thank you.
Okay, I agree.
Chris Thompson, UC Berkeley. To maybe follow up on that good point about public keys, have you considered promoting something like adding HPKP support into Android instead of having each app handle pinning code on their own, letting the remote origins set up the pinning that they want when anyone connects to them and doing that automatically?
Well, that, of course, HPKP is a good idea for browsers. But as much as I know, the deployment of HPKP still is pretty bad. So even for browsers, I don't know, just a couple of websites.
It's still it's still a very early phase standard, but looking long term, if we want to make smartphone communication security better, instead of just like a short-term engineering project, what are kind of long-term ways that either we could make the system better, like building this into Android instead of requiring people to do custom trust managers, which I've found is a little bit fraught with danger.
Yeah. But again, instead of trying to enforce some sort of pinning or HPKP, we think solutions such as certificate transparency or maybe next generation transparency solutions might make things a bit easier, especially for developers, because they get the benefits for free.
Okay, thank you.
Jaehyun Jung, Microsoft Research. So following on that, so from Windows 10, so certificate updates and pinning is now part of operating system. So I think his point has makes some sense. So my question is, so you said there are a few 40 apps that use pinning. have you looked at those apps to see whether they do proper validation and they have some right method there to update those certificates? Because there was a very large incident, like those Internet of Things, those hubs that had a like expired certificate that was pinned, so all those hubs went out offline. So the developers, they have like fear of this certificate management if they use pinning.
Mm-hmm.
So I was curious whether those apps, they had a right sort of update mechanism in place.
A couple of these apps were basically banking apps, and they had very strict security policies. And we actually contacted 2 of them, or could reach out to 2 of them, and they just had really strict security policies. And they said, well, we pin one certificate, and if things go wrong, we have to live with the fact that our users can't use our app for, I don't know, a couple of days or weeks. But they really just used one single certificate in a custom trust manager implementation, and hope that nothing goes wrong.
Okay.
Let's thank speakers one more time.
Mm-hmm.